Yeah. Okay. Yeah. So okay. So next speaker is Amir. Are you there?
Yes.
Are you there?
Yes. Can you hear me?
Yeah, we can hear you now. Yeah. Okay.
Okay. Cool.
You want to start sharing your screen?
Yep.
It's okay.
Can you see my screen?
Yeah, we can. Yeah.
Okay. Cool. So it's 15 minutes, right?
Yeah, you have 15 minutes. Yeah. So our next
Okay.
speaker here, Joudaki, will be talking about entropy maximization with depth and the variation principle for random neural networks. Yeah. Thank you.
Thank you. Yeah. Hello, everyone. I'm glad to be here, and I'm hoping that you would find this talk interesting. So, this talk titled "Entropy Maximization in Depth" and as a variational principle for random networks, it was done as the collaboration with Heidi Danishment and Princeton ACS and Francis Bach in ENS Paris. So let me just start by saying that the thing that every one of us knows, depth has become an essential part of of most state-of-the-art performance models across the board. So you have, for example, the accuracy of the various models going down over time, and you see that they get deeper for ImageNet and image classification on the top plot. And for example, as recently came out, protein fold prediction is also another, just purely from the point of view of layers, like it has 222 layers, and you have some other architectures, for instance, diffusion models, that is famously now introduced in Imagen, and many other very, very cool models that, and essentially they have infinite layers. So because they treat time as a continuous thing and not like as a discrete thing anymore. And perhaps the most interesting or counterintuitive at all is that depth is actually helping. And in particular, for instance, as the fourth paper points out, in many cases, depth actually helps generalization, which is pretty surprising because it adds so much to the expressivity of the model, but at the same time, in some regimes, it could actually improve the generalization, which is very, very counterintuitive. So these are the motivations for us to try to better understand depth. And that's the main objective here. So now why random networks? So here I just try to come up with some motivations of why studying random networks is actually a good thing towards understanding neural nets. The first line of argument is that randomness as basically our initialization point. So understanding them helps us to understand neural nets because as these papers, for example, the first paper shows that in an MLP, in a random network MLP, when you use that as your initialization, the hidden layer representations become highly correlated with depth. And that's a bad thing. And the second paper also points out that with actually normalization, the opposite happens, and that actually improves the training. So these are two line of arguments relating the randomness to our initialization point, and thereby its importance. But there's a second kind of perspective, which neural nets, actually almost random nets, could perform, meaning they could learn. And this is a very cool paper that they show that actually only training the batch normalization parameters, as opposed to the fully connected, or the CNN weights, could actually give you, 82% accuracy over CFAR and then 32% over ImageNet top 5 accuracy. So this is a very, very surprising result. And this is, I want to use this also as another argument for why understanding neural randomness is important, because perhaps understanding randomness is going to help us to like maybe study generalization essentially. So which is maybe a closer thing to the theme of this symposium. So because if we don't actually have to train so much, that's obviously going to be a good thing for generalization. So but this is not, I just wanted to use this as a motivation, but not actually, this is not the topic. Training is not, we only want to understand randomness. So before, like, let's just take a quick look at, what's out there so far. Like in current existing studies, there's a large body of work that relate random deep neural networks as Gaussian processes. And so here I'm pointing out the limitation of the current studies. And the main limitation of these line of work is that they all assume an infinite width regime. And that's how they derive their results. And there's another line of work that many different kinds, but there are many works that they assume a linear activation. So these works obviously also suffer from the fact that they cannot explain the realistic models. And another limitation of many studies is that they cannot or they do not consider normalization layers. So essentially, our focus for this work was a non-asymptotic analysis of a random net with a realistic setup. So realistic meaning it's non-asymptotic with width and depth, and it's also not limiting to linear activation, and it's also considering normalization. So that's the focus of our study. So let me just start by giving like a very quick overview to what is the direction, or what's the viewpoint that we want to take. So on the left hand, you see so you have a gas molecules that they behave in a stochastic way, but as a result of their interactions, we know that like the entropy is maximized. For instance, like that's what a Fokker-Planck equation describes the velocity or the position, depending on how you formulate the velocity of particles, and so the PDF of the velocity of particles. And when your molecules are derived, when it's governed, the interactions are governed by some Wiener process, the solution, they converge to the solution of the Fokker-Planck equation. So that's just, and it happens so that the equilibrium solution has maximum entropy. But we saw a very interesting work by Jordan that actually, so obviously when we're talking about a stochastic process here, time is continuous. But actually, there's also a discrete time stochastic process that leads to or converges to the same solution. So so Jordan gives this construction for this. So this led us to ask ourselves whether a kind of similar thing happens in random nets through layers. So if we view the layers as our stochastic discrete steps, because they're random, so like that's our change from one layer to another, do we observe some kind of an emerging phenomena, for instance, maximizing entropy? And without any formal definitions, I'm just gonna show the rough or like a very high level view of what happens. So from input to the deeper hidden layers until like very deep layer, like so this is actually our main observation, and I will give more formal meaning and definitions to what this actually plot means. But so now let's discuss so this is kind of like the view we took, that if we have this, you know, if we have this kind of emergent phenomena in randomness, it's basically, you know, it's imposing this as a prior for the randomness. So now let us discuss some more formally what we have. So this is a very, you know, I just to make sure it's clear, this is the MLP setup. So multi-layer perceptron has a width D and depth L, and the hidden representations are, for instance, you know, like there is a vector, and then you apply this activation, which is, you know, ReLU or, you know, tangent hyperbolic or any other thing, and then you have the multiplication, a fully connected layer. So this is your updates. Well, what we study is MLP with batch normalization. So the additional thing is that instead of processing with samples, you have you process with batches. And the major difference is that across each batch, you would make sure that the you zero out the mean and make them unit scale. So each feature is basically unit scale and zero mean through the batch, across the batch. So this is our setup. And before I state our main result, I just say the historical or our previous work that relate also the same problem. And the first one was where we studied the MLP, the normal MLP without batch norm. And the result was that the columns of these hidden layers become highly correlated. Essentially, the rank collapses almost to 1. And the second work is the MLP with batch normalization, and the exact opposite happens. So when you go deeper, the hidden layers become become closer to orthogonal, and the plot shows this fact. So starting from so the x-axis is layers, so 0 means input, and y-axis is the cosine similarity between two columns, and you see how starkly different these two behave. And like just to highlight the difference, actually we start the batch normed you know, network with a highly correlated input, and it actually manages to decorrelate it, while the opposite happens for the vanilla network. So this is our previous work. So so to state our main result for this work, these are the preliminaries. So the entropy, this is the differential entropy formulation. So that's how we define entropy. And we again have the Gaussian fully connected weights, and the input is taken to be this matrix, and of course the update rule. So the main takeaway here is that you can view the hidden layer representations as a Markov chain. So W being your random you know, transition, you transition from HL to HL plus 1 via this fully connected layer, which is your, you know, Markov chain transition table. And one thing that we assume is that we assume there is a stationary state, meaning that there is some mu that if, you know, H star follows that mu, then you wouldn't actually, your distribution, you wouldn't change under this layer update. And with that, now I can state the result, which is that the entropy of layer at some depth would be close to your maximum entropy, meaning, you know, entropy corresponding to maximum to Gaussian, that with this rate. So you have 3 essentially parameters. You have depth, which is exponentially decaying. So this is how much you're different from the maximum entropy. And you have also another term which depends on your batch size and width. And the most important actually term that it does not decrease with depth nor with width is your lambda, which only depends on your nonlinearity. So here, there are some insights from our proof that this is actually a constructed proof. So we actually build or approximately build this H star, which is stationary. And through that proof, we, for example, derive that for ReLU, lambda is 1/2, and for all odd functions, it's 1. So if you plug 1 into, you know, here, it's become 0. So you can always reach the maximum entropy with odd functions, but not with ReLU, which is, if you plug it in here, it's going to be 1. So here 1/2 would be log of 2, which means that it's reducing your entropy by 1 bit, which is very interesting because really we're zeroing out half of your output. So now with that, I would like to just show one again, like the results that I showed in the beginning, and now we can put like more meaning into this visualization, which is if you take the batch size 3 and you just track the hidden layers and plot each row as a dot, you would get this this visualization. So that's actually this demonstration that it is really becoming maximum entropy. And this is just another thing which is stating the same fact but using density plots. And obviously this is a very interesting result because this is just a randomness. So we didn't impose it explicitly, it just happened to be an emerging phenomenon. And I find it to be very interesting that, like given that this entropy maximum entropy actually happens in the natural world, like having it happen as an emerging phenomenon in a randomness is a very interesting pattern, and you can justify that if you don't have any evidence at initialization, this actually makes sense. And it is the best thing you can do. Like before you do any training, you have any evidence about your task, that the best thing is to have maximum entropy at your output layer. And one final thought that I'd like to say that it would connect it more to the theme of the symposium is, now we stated that the randomness are now from input to output. They map the input to something close to Gaussian. But does this actually encode anything? Like, is it just noise, or does it encode anything about input? So for that, we can actually draw samples from some, for instance, MNIST images, and then use them as input to your MLP. So you have again like an MLP. With, the only exception here is that we have strong residual connections. So you create this noises, essentially noise vectors, Z. And then we can actually ask, like, can we actually train or reconstruct this X back? And the surprising answer is yes. So while MLP is completely random, this inverse function is actually learned. So it's just like a training process. And here I'm showing just a recent result, which we see that actually does recover to some extent the input, which is very surprising because we didn't, again, we were not touching, or we're not imposing this, this process to be invertible, but somehow it is. And I think that that also tells us something about whether there is a more meaning to this entropy maximization, for instance, whether it could be connected to optimal transport. So you can argue that, maybe conjecture that the way that these point masses are mapped to something like a Gaussian distribution is not any map, but it's actually close to some optimal map. So that obviously would imply like a shorter Kolmogorov complexity, because describing that this something is as an optimal, then there's an algorithm for that. And with that, I'd like to finish and thank you for your attention. I'm very happy to take any questions.
All right. Any questions?
Do I need that?
Yeah, just...
For the model shown in the end, doesn't the residual connection lead to some of the information being retained by the first one, though? Because you've said it's random and that you're not training your encoder, but you have a residual connection in it that is likely to pass through information from the input to the output, right? So you're not going to lose everything.
Well, it's so that's true, of course, but this is 100 layers actually. So I mean, this is taken to be like as a visual evidence. I mean, this is not yet, this was not part of our main work. This is just a speculative, we can say it's a conjecture. Like you see that here, of course, there are some structure, but we don't, I mean, I don't see the numbers here. Like, and it's just basically, I'm asking myself and you, like, whether this randomnet behaves like an encoder. So yes, you're right. I mean, like, that's exactly why I introduced this residual connections. But at the same time, this thing is pretty close to random. And it's, I mean, you can probably measure that, you know, how close it is. And I'm arguing like that if this is close to random at the same time as keeping some bits about input, that tells us something about, you know, what this result, this maximum entropy could mean.
Thank you. Yeah, thank you.
All right, thank you. Any other questions? Yeah.
Thank you. Yeah, maybe a small, simple question, but the title of your talk is a variational principle maximizing entropy.
Yeah.
So I slightly missed where the variational principle comes in. Can you highlight that for me?
Sorry, was that a question? I mean, I don't hear anything else.
Yeah. Can you hear me? Let's start there. Did I mute myself?
He froze.
Oh, great.
All right. Okay, so let's resume for at 1:30. Next talk at 1:30. So we'll have shorter. Yeah. Right.